Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 84. Now in the previous lecture, we were discussing about various aspects of prebiotic chemistry, and I had ended the lecture by talking to you about the significance of water as a solvent which mediates chemical reactions, and how that plays a vital role in the way life has evolved on Earth as it is today. We were discussing about two major points. The first point was about the broad range, in which water can exist as a liquid. That supports a wide variety of chemical as well as biological activities. And the next point we discussed was about the density of ice water vis-a-vis the density of water liquid. Typically, you would expect a solid to be denser than a liquid, but in the case of ice, until 4 degrees, ice is denser, and that is why an ice layer floats. It doesn't freeze the liquid completely. So aquatic life and a lot of chemistry which uses water as the solvent at very cold temperatures can also happen. Now we shall be discussing about two more points in this lecture pertaining to water as a solvent and its significance, and followed by that I will introduce you to the last topic in this course, which is about chirality. All right, so the next point about water, the significance of water. So continuing from lecture 83, the water also has the following interesting properties. We were looking at the first two properties, which were concerning the broad range of temperature wherein water exists as a liquid, and the density of ice versus the liquid phase of water. The next point is water is a highly polar solvent. Now I'll leave it to you to figure out what polar means. I think we've already discussed in the context of molecules having dipole moment when discussing rotational spectroscopy, how molecules rotate, vibrate, etc. Okay, so bipolar, we're talking about the molecule having a finite dipole moment, and it contributing actively to the creation of some sort of an electrostatic interaction, an active electrostatic interaction. Okay, so that's the overall meaning of polar. A molecule being polar, and the concept is broadly called as polarity. All right, so water is a highly polar solvent. Now what this does is, what water's polarity does is, it gives rise to to a variety of layers in chemistry and biology. For example, you may be recalling that probably from your high school onwards, when perhaps discussing about the action of soap on bodies, the action of micelles or micelles, and the concept of hydrophobicity and hydrophilicity. What does that arise due to? All of them arise due to the notion that water is a polar solvent. So because water is a polar solvent, it creates some layers. And due to these layers, what happens is that, I'll continue here, the layers, for example, hydrophobic and hydrophilic, etc., right? They give rise to what is called as multi-phase chemistry. And because of multi-phase chemistry, you can have structures such as, for example, your membranes and other layers, other porous layers in the body, right? Wherein you can have compartmentalized chemistry and biology. Compartmentalized biologically important reactions. Biologically, IMP stands for important reactions. So therefore, water being polar not only allows for the chemistry of water itself, but by creating various layers due to the notions of hydrophobicity and hydrophilicity, it extends the scope of chemistry associated with water even in the hydrophobic region, that is, the layer of which water is not a part of. All right. So therefore, water being polar is also extremely important for the wide diversity and different types of chemistry that can be found on Earth, all of which eventually lead to various forms of life. Okay, so this was the third point. The last point is associated with the large heat capacity of water. Now, what does this do? Now, your heat capacity, typically denoted by the symbol C. It depends on whether we're concerning ourselves with a constant pressure scenario or a constant volume scenario. Let's not go there. Okay, that will be a hardcore thermodynamics class. I'm just generally calling it C. Okay. Now, heat capacity refers to your C. Okay, is a measure of how much heat is needed to raise the temperature of a substance by 1 degree Celsius. I mean, 1 degree Celsius, the difference between Celsius and Kelvin is the same. So, convenience, I'm using Celsius here. Okay, there's a need to raise the temperature by 1 degree Celsius. And of course, it depends on the amount of substance that you take. In the case of water, for example, for water, your C is given by, if I'm correct, around 4.2 per gram per centigrade. All right. So this is the value. Okay, 4.2. It's the amount of heat, right? So it should be some energy. This is the definition of a joule. Yeah. So this should be 4.2 joules per gram per centigrade. All right. This is how much heat energy is needed to raise the temperature of water by 1 degree. And this amount is a reasonably large number. Please note. In the context of other solvents, this is a significantly large number, right? And so what it does is it regulates the temperature. So this leads to regulation of the, I think in the literature of astrobiology and a lot of biology and medicine also, the phrase for the technical phrase for this is what is called as homeostasis. In other words, how well are you able to maintain any given temperature, right? So, see, water has this astonishing quantity. It can be a liquid in a broad range of temperature, but yet once any given temperature is established as a result of mechanical equilibrium, mechanical and thermal equilibrium, what happens is that it is not so easy to change from that temperature. In other words, you need a substantive amount of heat. This results in the regulation of temperatures. So therefore, this gives rise to the concept of chemical reactions and forms of lives. So chemical reactions happening at a particular temperature, chemical reactions at some particular temperature, and the forms of lives adapting to a given temperature. And over many years and eons, the human body temperature is roughly around 38 degrees C, right? Or 98.4 degrees Fahrenheit. We say that Well, if the temperature raises above it, someone has a fever. That is where homeostasis is no longer in our control. So the point being that water helps in the regulation of this temperature, and which is a very important feature for not just biological forms, but also for chemical reactions happening at some constant temperature. All right. So these are some representative ways, some amazing representative ways via which water plays a critical role in the sustenance of life on Earth, starting from small life forms, going all the way to the evolution of chemicals leading to life itself. Okay, so this was about water. Our next and last topic for this course of astrochemistry is going to be the idea of chirality. I will go, in a bottom-up way for this, okay? Because we are talking about prebiotic chemistry. What we know about chirality on Earth. What is chirality? Well, a lot of chemistry majors and quite a few, physics students are also aware of chirality. We also discussed this, the idea very briefly, probably, somewhere in the early 20 lectures when we were talking about the molecules detected in space. Okay, so chirality can be attributed as, this is a working definition, the ability of any molecule to rotate the plane polarized light. This is a working definition. It's given by optical activity. Now, chirality refers to asymmetry, and in terms of experimentally measurable quantities, it relates to the ability of any molecule to rotate the plane of plane polarized light. Now, what is plane polarized light? I'll quickly give you an understanding. So, let's say a source emits light. Okay, a source emits light, and light just doesn't travel in one way, because we're not talking about a point source, right? It's not an ideal point source. So light travels in all sorts of, there were lots of light rays emanating from the source and reaching any object. There are some special substances, if you put in the path of these light rays, all the light rays happen to be, contained in one plane. That's amazing. So such a light is what is called as plane polarized light. Okay. Now, when this plane polarized light is actually in the, let's say you put a chiral molecule in the way of plane polarized light. What happens is that the plane of the plane polarized light, there should be one plane wherein all the light rays are contained, right? That rotates. That can be measured by what is called as optical activity. Now, what sort of molecules exhibit chirality? One predominant form of chirality is what is called as your point chirality. There are, of course, different types of chirality, but I will just talk to you about one form of chirality. This is what is called as chirality due to, you can call it point chirality, or in the lingo of chemistry, due to, I don't want to use the phrase chiral atoms themselves. I want to use the phrase due to specific atoms. What's an example? This is what is referred to as point chirality. Okay. Example, you take a generic amino acid structure. Let's say, that this is the two-dimensional representation of a three-dimensional structure. Let's say you have your this is the general structure of an amino acid where R is not equal to H. This is what is called as a Fisher projection. But what this tells you is, I take a tetrahedral species. See, tetravalent carbon is going to have a tetrahedral structure. Now I project it onto two dimensions, I get this structure. Okay. Now, when I take its mirror image, just denoted by this, the top and the bottom remain the same, and the right and the left get flipped. So this is going to be NH2, and this is COOH. So this is an example. Of course, here also R is not equal to H. So this is an example of a chiral amino acid. such that the two mirror images are what are called as the two enantiomers. We're going to call this as E1, E2. So let's say that your E1 rotates the plane of the plane polarized light in one direction. Your E2 is going to rotate in another direction. Okay. So if the plane of plane polarized light, I'll just call it like PPL, is rotated to the right side, we get what is called as the dextrorotatory, okay, right, molecule. Let's say this dextrorotatory enantiomer. So one enantiomer is supposed to rotate the plane of plane polarized light in one way, and the other enantiomer rotates it at another way, okay, in the opposite way. So if there can only be two ways, right, in which the plane of polarized light can be rotated. So this is going to be called as dextrorotatory, and if the same plane of PPL rotated to the left, we get what is called as levorotatory. These are, I think, German words, okay, German or French, I forget. I have to check and tell you. So this is levorotatory, and this is this is dextrorotatory, and this is levorotatory, or perhaps like Greek and Latin. I don't actually know. Okay, yeah, I'll have to go and look back and tell you. So this is dextrorotatory, and this is levorotatory. So one enantiomer could be called as a dextrorotatory molecule, and another enantiomer could be a levorotatory molecule. Now, what happens on Earth is that what we know from biological systems. So, by the way, this was a very simplified and a layperson's introduction to chirality in just 2 or 3 minutes. Okay. In fact, in subjects such as organic chemistry and biochemistry, chirality is a vast ocean. It's a whole lot of details I've skipped. For example, I only talked about enantiomers. There are going to be molecules called as diastereomers. There is also, some kind of an arrangement where you can have point chirality, that is chirality due to specific atoms, but the overall molecule not behaving chirally, etc., etc. All those cases are there, but I'm going to skip them in the interest of time. Just get to know the broad details of chirality, the broad idea of chirality, and for more details, you can always look up an organic chemistry textbook, okay, which it is not hard at all. It's quite easy. Okay, now having given this introduction, the fact about chirality is that in a lot of biological systems, predominantly the L amino acids are found almost exclusively one beauty about these enantiomers is that, beyond rotating the plane of the polarized light, their physical properties are very similar. Okay. So despite the identical, in fact, almost all other physical properties are identical, but for their ability to rotate the plane polarized light. Okay. The direction in which, not even the ability, the direction in which the plane polarized light is rotated, that is different. So despite, despite having such similar properties, right, on almost all accounts, yet in biological systems, the L form predominates. The question is, why is it? This, in fact, is an open question in the area of prebiotic chemistry and astrobiology. Okay, we don't know the answer yet. It's an active area of research. Now, this concept of one particular version of a chiral molecule predominating is what is called as homochirality. And what is the origin of homochirality? Well, why? No one knows yet. No one knows yet for sure. Although, at the PhD and research levels, lots of research is being done in this direction. We don't know precisely that, this is why homochirality predominates. Okay, so this is homochirality as far as biological systems on Earth is concerned. Okay, right? Now, what about the solar system? We were discussing about meteorites, we were discussing about meteorites and then asteroids, comets, etc., right? Now, this is homochirality, and this is on Earth. Okay. Now, in the solar system, if you recall our discourse on the chemistry of meteorites, I kept referring to a meteorite called as the Murchison meteorite, right? The specialty of the Murchison meteorite is that the solar system, especially, as we get to know from the Murchison meteorite, chiral alanine, which is given by your CH3H, COOH, and NH2, right? Chiral alanine with L form, in slight excess. Notice this point, it is in slight excess. Whereas while we talk about the biological systems, it's almost exclusively the L form. Okay, right? I'm talking about less than 10% was found way back in 1980s. So people were thinking that, oh, perhaps this may have occurred due to contamination with Earth, some alanine on Earth. Okay, but then later on, it was also found that the L form of another amino acid, which is rare, okay, which does not occur on Earth, which is called as, that has a structure of your COOH and H2. I'm just drawing one enantiomer, okay, H, and here a CH2CH3. So the L form of isovalent was also found in slight excess. So how did, again, the key word is slight excess. So in the meteorites, that is in the solar system, the idea of chirality is known. But the chirality stage, the chirality has not progressed into the homochirality stage. That's important. So in the meteorites, that is as part of the solar system, right, some chirality is known, right? This particular term, the dominance of, or the excess of one enantiomer over another is what is called as an enantiomeric excess. Okay, this is what is called as EE, or I'll write it down here. Excess of one enantiomer is what is called as an enantiomeric excess. Enantiomeric excess. Okay, I'm not writing it the full form, but I mean for simplicity. So enantiomeric excess. Now in the solar system, slight excess, slight enantiomeric excess is noted. In fact, this was around 80s, this was around the 1990s, if I'm correct, 97. But in 2018, okay, in 2018, very slight enantiomeric excess of, this is propylene oxide, was also noted in the same Murchison meteorite. I'll just call this MM. So all these ideas tell us that the concept going towards homochirality, that is a slight enantiomeric excess, is always noted in the solar system. But how to go from a slight excess to a dominance of one particular enantiomer? That's a very open question even today. Okay, all right. Now you look at this specific molecule. Does this ring a bell? Have we looked about or seen about this molecule anywhere? All recall that? I think if you go back to probably around lecture 19, 20, I mean 15 to 20, somewhere there, right? I told you that this molecule was the first molecule which could be chiral. That is, both the enantiomers of this molecule, okay? Both the enantiomers of this molecule, note, both enantiomers of this molecule, propylene oxide, was detected in the ISM in 2016. I told you, right? Detected in the interstellar medium in equal amounts. So it's already fascinating if you think about it, right? In the ISM, chirality is not generated. Instead, we only have the situation called as prochirality. That is, prochirality is the condition which leads to chirality. It's one step before chirality. Now that is already known in the ISM, the concept of prochirality. But enantiomeric excess is not registered in the ISM. It has not been detected in the ISM yet. However, when we come to the solar system, there is some enantiomeric excess. And when we go all the way to Earth in biological systems, homochirality predominates. All right. So what does this tell us? This tells us that, in fact, how did chirality overall originate? Did it originate in the interstellar medium? Or did it originate, somewhere while the solar system was getting formed? Or did it actually happen to be a major player, a dominant player with substantive homochirality only on Earth? These are open questions. These are extremely interesting topics. One proposal for how enantiomeric excess could originate in the ISM is that, see, this molecule has some protons, okay, is that elastic proton-proton scattering. We're talking about the protons in this molecule, right? And there are also protons here. I'm just not showing them. This versus the cosmic rays. Remember, cosmic rays predominantly contain a lot of proton streams, right? So the proton streams, we're talking about non-local thermal equilibrium conditions, and they are highly energetic. And so, under this non-equilibrium condition, this elastic proton-proton scattering could selectively scattering between the protons of this molecule. Let's say the prochiral molecule, that is the chiral molecule, sorry, which came about as a result of prochiral chemistry. Okay, right? So this chiral molecule whose enantiomers are found in equal amount. Now, when it is subject to proton-proton scattering, selectively, one enantiomer gets destroyed. I'll write it down here. Gets destroyed. This is so elastic proton-proton scattering, proton from a chiral molecule, but whose both enantiomers are present. Once it is formed, right? Proton-proton scattering with elastic scattering between the protons of this molecule and the proton from cosmic rays, that could result in enantiomeric excess. This is one proposal. This is a proposal, no this keyword. Okay. So this could perhaps be the way through which, a small amount of enantiomeric excess is generated in the solar system, and which eventually gets amplified all the way on Earth. But how this happens, no one knows. Okay, right? And this is in fact one vast area of study, the origin of chirality in space. I mean, and how is it connected with the chirality that is so important on Earth? So on that note, right, we end our brief discussion about prochirality, chirality, and homochirality. And with this, I conclude the course formally. In lecture 85, I will just give you a summary of this course in an epilogue or perspective type way, and tell you what entails after this course. For example, what course one could take, and what was the logic behind the modules chosen, etc., with this course. On that note, I end this lecture. And the brief summary for this course is, well, I introduce you to the ideas of chirality, prochirality, and homochirality. And before that, I was talking to you about the role of water. I started off with this in lecture 83. In lecture 84, I concluded the significance of water in mediating chemistry and biology on Earth. So thank you so much. I'll meet you in lecture 85.